In this video we will demonstrate metamaterial diffraction in microwave frequency. Previously, it was shown that an aluminum plate, which virtually reflects all of microwave power, didn't show any observable diffraction effect. This time, we will test if diffraction effect can be observed in a partially transparent obstacle which is constructed as metamaterial. The metamaterial obstacle is made from an array of aluminum stripes 200 x 5 mm with 0.1 mm thickness. The gaps between adjacent stripes are 5 mm. The stripes are held fixed at their positions using a corrugated plastic board and bonded using double tapes. The diffracting edge is kept clear from plastic materials to make sure that the diffraction is produced by the aluminum part. Although, our tests show that the plastic parts don't affect the transparency of the obstacle significantly. Let's see how the obstacle affect microwave transmission. When the edge is right at the middle of transmission line, 90% of microwave intensity reaches the receiver. It varies when the obstacle covers more transmission area. Small interference effect can be observed when the obstacle is moved back and forth, which is the result of superposition between direct transmission wave and the reflected waves, which are produced by the obstacle, transmitter antenna, and receiver antenna. The interference effect can be suppressed by turning the obstacle at an angle to the transmission line. When the aluminum stripes are oriented vertically, most of the microwave intensity is reflected instead of transmitted. Interference effect is also observed when the obstacle is moved back and forth. Just like before, the interference effect can be suppressed by turning the obstacle at an angle to the transmission line. Now it's time to demonstrate the diffraction effect. The receiver is relocated to a position out of transmission line, which makes the intensity reading close to zero. When the obstacle is put in place with the edge at the transmission line, the receiver shows an increase of intensity. As seen here, the receiver is located in the shadow region of the obstacle, which is the defining characteristic of diffraction. Starting from the previous setup, the receiver is rotated to horizontal polarization. The intensity goes down to zero. When the transmitter is also rotated to horizontal polarization, the intensity increases very slightly. When the receiver and transmitter are rotated to diagonal polarization, the intensity is still close to zero. Now the position of the transmitter has been moved closer to the obstacle to get highest intensity at the receiver. The effect of interference can be reduced by turning the obstacle so it's no longer perpendicular to the transmission line. The intensity reading is lower than before. Adjusting the position of the obstacle cannot increase the intensity to the highest level. We get the same result when the obstacle is turned to the other direction. It seems that diffraction effect can be enhanced by involving interference.